Hi
Hey
guys, here we are, just Princess Peach and
Donkey Kong.
I don't know that he makes really good noises.
No, I know, yeah.
So we're just here in the land, Mario Land, of course, you know, wandering around, and we figured we'd talk to you about the reaction rates in a chemical reaction.
Why not? Makes perfect sense.
So let's take a look. So first of all, we just want to talk about what is chemical kinetics.
Ooh, fancy words.
Yeah, so this is just a study of things that affect the rate of reaction.
Okay.
Okay. So, for example, like a reaction rate is the rate at which the reaction takes place.
So how fast or slow it goes.
Exactly.
Okay.
Okay. And then that is basically measured just by the disappearance of the reactants and the making of the products.
Okay.
Yeah.
Nice and easy.
Yeah. Okay. So here's some things that cause a reaction. Are you ready?
I'm ready.
Boom. You need particles to run into each other.
Okay, so it's not magic, doesn't occur over distance.
Right.
Particles actually have to collide.
Right. In order for a chemical reaction to take place, they have to bump into each other.
Boom.
Like that. Exactly. Perfect. I'm sorry, that had a little much
Yeah,
little force behind it.
Yeah, not ready for that.
All right. They also need a minimum amount of energy to collide. So there's a certain point at which they need to like basically get that ball rolling.
Gotcha.
Okay.
So they need to hit each other, and they need to hit each other hard.
Pretty much. Yep.
Okay.
Yes. Okay. And the collisions have to have some energy.
Okay.
So not only do the particles have to have energy when they run into each other, but the collisions themselves have to have some energy.
Okay, so like if particles can have energy, but they can't be traveling in the same direction, right? Because then they would collide and just kind of
bounce off. Right.
Yeah.
We need them to
boom, opposite direction, head on. Okay.
Head on crash if you're talking cars. Okay. So what is the collision theory exactly? And it just states that as more collisions in a system occur, there'll be more combinations of new molecules.
Okay, so they collide, they react.
Yes. So kind of like, say you're in a very small school. Let's say there's only 100 kids.
Yeah.
Okay. You're not going to have nearly as many dating options. Let's go with that. Okay.
Okay.
If you go to a bigger school where you have, say, 1,600 kids, the options are a little bit more, you know.
Yeah.
Yeah, more options. All right. So some things that can affect the rate of a chemical reaction. All right. Number one, the concentration.
Okay.
So, like how much or how little of a reactant you have.
Okay, so that makes sense. If I have more of something, they're going to collide more often. And more of them will have the appropriate amount of energies and the right collisions and all that stuff.
Exactly.
Okay.
I kind of look at it like a crowded lunchroom versus an empty lunchroom.
Okay.
Okay. So sometimes if it's a crowded lunchroom, you have the possibility of bumping into people, which causes people to get angry, which in turn then turns into a all-out brawl or food fight. One or the other.
Yeah, one. Yeah.
Mostly the brawl.
Yeah.
But so the more people, the higher the concentration of individuals, the more collisions that'll occur.
Okay, makes sense.
Yeah.
Sure.
Some more factors we have is temperature. Okay, so you increase the temperature, those particles are going to move faster. Therefore, they're going to collide more often.
And also, they're going to have more of the energy, right?
Exactly.
So they collide, and they're going to be colliding with more force. So
more energy release, kind of like when you hear someone that has talked mad smack about you, or if you will, and then the next thing you know, your emotions are running hot, and you see that person in the hallway, and then you look like those two guys on the floor, one missing a tooth, one with a black eye.
That's brutal.
Yeah.
I don't think anyone's talked mad smack about me in a while.
No, I can't say that either. So then the last one we're going to talk about here is surface area. Okay, so surface area is referring to how big or small the surface of the particles are.
Okay.
So it's a good example of that.
So you got some mints here. So if you have a mint whole, it takes a lot longer to dissolve, but when you chew it up,
it goes really fast.
Smaller particles, more surface area, more area to react.
Exactly. Kind of like our Tootsie Roll owl here. How many licks it takes you to get to the center of a Tootsie Pop? Well, it only took him 3 because he bit into it.
That's the answer.
So otherwise it would take a lot longer. Okay. And then we have some graphs we're going to take a quick peek at. Okay. So each curve represents the different rates of change in a chemical reaction. So here we have N2O5, NO2, and oxygen, all represented with different colors.
Very pretty.
Okay. The curve of the reactant will always have a negative slope because the reactants are going to eventually turn into products. So if our reactants have a negative slope, our products should have a
positive slope.
Absolutely.
So our reactants are being used, our products are being formed.
Yep.
Makes sense. Okay.
Okay, so and basically any time you can look at the slope, it talks about what coefficient goes in front.
Ooh.
I know it's a little intense.
Fun.
We're not going to get too far. Just kind of talking to you what it's going to look like.
Sounds like fun.
Okay. All right. So in order for a reaction to occur, you need to have some of what we call the activation energy.
Fun stuff.
Okay. So if they don't have enough energy to collide, they're kind of in this stuck pattern.
So this would be like them colliding, but just kind of bouncing off, not really hitting each other very hard. So they need really a lot of energy to kind of pound and collide and react.
Yes, exactly.
Do what they gotta do.
This would be kind of like when you're walking in the hallway and somebody accidentally does one of those.
Yeah.
So.
Gotcha.
Okay. So what happens is that complex, once they hit that part, that gives them that energy, and then boom, then they turn into products.
Gotcha. So we have two things. They kind of hit for a split second. They're kind of together-ish, that activated complex, and then they break apart and make their products.
Absolutely.
Gotcha.
Okay. So some examples of those could be a flame, could be a spark, a high temperature, something to get that
going.
Yes,
Something
exactly.
to add that activation energy in.
Okay. So then, of course, we have two types of processes. We have exothermic and endothermic. Exo meaning heat is
Exited or released.
okay, and endo meaning
The opposite, it's consumed.
absolutely.
So exothermic or hot.
Absolutely right. Yes. Okay. So where energy is being produced as a product. Okay.
Fire.
So it's warm. You.
No, I got there. Yeah.
All right. So it's released, and you can see that in this case, the energy of the reactants is much higher on the graph than the products because the energy is being released.
Okay.
So when your products are formed, it's out of that system, and well.
So that energy has to go somewhere.
Correct.
Right. Our reactants have a ton of energy. Our products have very little. That extra energy is released in the form of usually heat
or light or sound or some kind of thing like that. Yeah. Okay. So then the endothermic type of reaction, you have to put heat into it in order for a reaction to occur.
Okay. So these would be cold reactions. Reactions that would make
right.
things colder.
Exactly. Kind of like those when you break them, packs.
Oh yeah, the chemical ice packs.
Yes.
Yeah.
Okay. So like when you fall and you hurt yourself in PE and they want to put ice on it and it's cold.
Gotcha.
Okay. So that would be our example there. Okay, and then the last thing that we need to talk about is the catalyst. And the most common one that you've all have probably seen is what we call the elephant toothpaste. See the elephant? He's got his toothpaste at the top.
It's not real toothpaste for elephants.
No,
just
not that
be aware.
good.
Yeah.
Okay. So what the catalyst does is it speeds up the reaction, and what it does is it lowers the activation energy to get it started.
So you need less energy, so more particles would have the amount of energy. The collisions don't have to be quite as hard.
Exactly.
Got it. It's just easier for everything to take place.
Right, yeah. So basically all it is doing is it's giving that reaction a little extra shove to get going.
Gotcha.
Okay. Click there. Should be some more. There we go.
There it is.
So basically it just kind of, the products are going to be the same. That catalyst doesn't affect what products are coming out. It just gives it a little extra push.
Gotcha. Okay.
Okay. I kind of feel like it's a coach. Like, get it, team. Okay. And it speeds up the reaction. Okay.
Okay.
All right. Well, that's all we got for you. So we'll check you later.
Bye.